In this video, we're going to prove that given any real number, we can find a larger natural number. This is called the Archimedean Principle of the reals. So this proof is going to use what we called earlier the alternate completeness axiom, which says that non-empty sets of reals that are bounded above have a least upper bound. In other words, if S is a set of real numbers and S has at least one element and S has at least one upper bound, then there is a real number that acts as a least upper bound of the set S. So we're going to use that during our proof of the Archimedean principle. So to precisely state the Archimedean principle, it goes as follows. If R is a real number, then there's a natural number n so that R is less than n. Okay? So for any real number, we can find a larger natural number. That's what we want to prove. And we're going to prove it by contradiction. So let's assume, by way of contradiction, that there is some real number so that there's no larger natural number. In other words, we're suppose that there's a real number R, so that if n is a natural number, then n is less than or equal to R. Okay, so R is an upper bound of the set of natural numbers. Okay, and if R is an upper bound of the set of natural numbers, remember the natural numbers is a subset of the real numbers. We can identify it with a subset of the real numbers. So that means that the natural numbers is actually a set of real numbers with at least one element. Okay, 0 or 1, 2, 3, so on. It's got at least one element, and it's got at least one upper bound. So that means we can apply the alternate completeness axiom and say that it has a least upper bound. So let's call that least upper bound S. So we know a couple things about S. Since it's a least upper bound, we know that it's first of all an upper bound. So if n is a natural number, then n is less than or equal to S. And we know it's the least upper bound. So if u is another upper bound of the natural numbers, then n is less than or equal to u. Okay, we don't know. Sometimes it gets confusing. You might think that S is itself a natural number. We don't know that. It's just a real number. The alternate completeness axiom guarantees us a real number that is a least upper bound of the set, but that may not be in the set. Okay, so all we know about S are these two things. It's an upper bound and it is a least upper bound. This second condition, we're going to reformulate it as saying that if you have a real number smaller than the least upper bound, so if you have a real number smaller than S, then it can't be an upper bound. If it's smaller than the least upper bound, then it's not an upper bound. So we're going to use that formulation applied to S minus 1. S minus 1 is less than S, so that means that S minus 1 can't be an upper bound of n. It's not an upper bound of the natural numbers. Okay. Now think about what that means to say that S minus 1 is not an upper bound of the natural numbers. Well, if you were an upper bound, all the natural numbers would be below you. But if you're not an upper bound, that means there's a natural number above you. Okay, so there's at least one natural number, let's call it m, so that S minus 1 is less than m. Well, that means that S is less than m plus 1. And that seems to be a problem. Remember that m is a natural number, and 1 is a natural number, so m plus 1 is a natural number. And S is an upper bound of the set of natural numbers. So S is above any natural number, so in other words, m plus 1 should be less than or equal to S. Okay, so the problem is, we have now m plus 1 is less than or equal to S on the one hand. On the other hand, we also have S is less than m plus 1. Okay, so that's a contradiction. We have m plus 1 is less than m plus 1. That's a contradiction. So that means our original assumption has to be false. Our original assumption was that there's some real number that's an upper bound on the set of natural numbers. Okay, so we initially assumed that we could find a real number so that all the natural numbers were below it. That led to a contradiction, so that assumption has to be false. If that assumption has to be false, then the opposite of that assumption is true. In other words, if you have a real number, you can find a natural number larger than it. So that concludes the proof of the Archimedean principle. Thanks for listening.